Okay, so let's talk about vectors. So, magnitude and direction. The speed and direction of a plane and the wind can be represented by vectors. So, have you ever seen, the best explanation for this is, have you ever seen, okay, so have you ever seen on the Weather Channel or when they're doing the weather where sometimes there'll be arrows on the map?
Oh, yeah.
You ever wonder what that is?
Vector.
Those are vectors.
I knew that.
Did you? No.
My mom told me.
So they're vectors, and the longer it is, the longer the vector is, right, the more magnitude it has. Okay, the stronger, exactly. So that kind of makes sense, right? Okay, so let's talk about vectors. So a vector is a quantity that has both magnitude or length and direction, and is represented by a directed segment. So this is a vector. So the standard position of any vector is at the origin. I'm going to write at origin. Okay, so we have a vector. It means magnitude and direction. Vectors can be, the component form of a vector is with this type of bracket, and it is the change in x, comma, change in y. So that would be component form. And that'll mean a little bit more to you in a moment here. So equal vectors. Two vectors are equal if and only if they have the same magnitude and direction. So which one of these vectors down here are equal? Z and B. They're going in the same direction, and they are equal magnitude. Parallel vectors. Two vectors are parallel if and only if they have the same or opposite direction. Okay. Y and W are going opposite directions, right? But they are parallel. V and W are also going in the same direction, right? The exact same direction. That's about it. Y and W, V and W, V and Y. Z works too, yes. Okay? So this one has greater magnitude than this one. These both have the same magnitude, but they're going in opposite directions. All right, write the component form of AB. So I said the component form is change in x and change in y, correct? I'm going to write that out, delta. Delta x and delta y means change in x, change in y. Okay, so my change in x. How much do I change when I go from A to B? -5 and -1, correct? So -5 minus -1. Why would I say minus -1? Distance means difference. The difference between the two, right? So -5 minus -1 is -4. Now all I have to do is make sure I began here, right? And I compared -5 and -1. So when I'm finding my change in y, I also have to begin with B. So it'll be -1 minus -4, which equals 3.
Oh, so minus.
Yeah, the difference between. Yes, you could just count them. And the only reason I'm showing you this is just because this is what you would see in your book. I would normally just count them. I would just count them, and then I would look at my direction. This direction is in the negative, right? It's a negative slope. That's why I've got a negative here. And some teachers would argue with me and say that this is the absolute only way because, and I'll show you why right now, when we do slope formula, isn't the technical slope formula y2 minus y1? Now, I would argue that it doesn't matter because isn't this answer the same as, oops, definitely not, the same as this answer? They are the same thing, and that's why I would argue that you don't need to know which one's negative, you just have to know that the line is negative. Correct? I would say, how far do I have to go to get over here on the x? 1, 2, 3, 4. How far do I have to go up? 1, 2, 3. Okay, so let's write the component form. So it's written like this. What is my change in x? -4. And what is my change in y? 3. So that is the component form of this vector. It stands for how far of the direction I'm going on the x and how far of a direction I'm going in the y. This is not a point, right? That's why the brackets are different. All right, let's move on. Find the magnitude in the direction of st for s being at -3, -2, and t being at 4, -7. Okay, magnitude means length, right? How do we find length? Distance formula. Magnitude equals length. So I'm going to say, what is the distance or my change in x? What's my change in x? 1, 2, 3, 4, 5, 6, 7. And my change in y? 5. One of them's got to be positive and one of them's got to be negative because this is a negative slope. You'd make the 7 negative?
I'd make the y negative.
I'd make the y negative too. Now this is where it changes. If I wanted to write this in component form, I would have to pick one, right? You pick the y? I would pick the y as well. But if you would do it y2 minus y1, it's the 7, isn't it? So that's why I would say this is the same answer to me as this. Correct? It's the same slope. So this is component form, but that's not what they asked us for. They asked us for magnitude. So I'm going to use my distance formula. So my change in x is -7, and my change in y is 5. Square both of those, and I get the square root of 74. Find that, and it's about 8.6. So this vector has a magnitude of 8.6.
These things just don't go away, huh?
No. Oh, well, you just wait and see right now. Direction! This is where it gets fun. I didn't say this lesson was easy. All right, direction. If I want to find the direction that this vector is going in, I need to figure out, let me see how I want to do this. Do I want to confuse you now or later? Now? Would you rather be confused now?
Yeah,
Okay, let's do it.
Piss me off right now.
Okay, this vector has direction, no matter where I put it, right? Is it still going the same direction? Well, let's put it in standard form. Where's standard form again? Standard position, I'm sorry. At the origin. So right here. Correct? So to figure out its direction, how do you think they measure direction when you've got planes in the air? How do you think they find direction? What does a compass, what does it measure? What's the unit? Degrees. If I need degrees, wouldn't you say that this this is the first quadrant, right? This is the second quadrant, this is the third quadrant, and this is the fourth quadrant to make 360 degrees. This is why in math we go counterclockwise. Because on a coordinate grid, don't we start here in this coordinate and in this quadrant? So if I were to go all the way around, it would be 360 degrees. I don't need to go all the way around. I just need to go to here. Okay? So, if I want to find this angle, I'm going to find this angle here. Why would I find this angle here?
Which angle are you talking about?
I'm going to subtract it from 360. So I'm going to find this angle right here. No. If this angle is what I'm looking for, aren't I looking for this right here? Isn't this line right here parallel with X? No. No, it is not half of 90. No, there's not. It's not the same space. And you can't just automatically assume that, for sure. See that? I put it more in standard position, and is that going to be 45 degrees? Absolutely not. Okay, so that being said, yes. Knew it was coming. You guys are going to complain. Tangent theta equals what? Opposite over adjacent, right? I know my opposite over adjacent. But when I'm trying to find the angle, I don't use tangent, I use inverse tangent. So the inverse tangent of, what's my opposite? We already found it. It's 5 over -7. If I put that in a calculator, so you need to write this too. Make sure you consider whether it's positive or negative, right? Because that makes the difference. When I put this in a calculator, I get -35.5, which makes sense because don't we have to subtract it from 360?
I thought you can have a negative degree.
This is going in the negative, right? Technically. If you look at it that way, isn't it going in the negative? So that's why you get that answer. You get a negative answer because it is negative by that much. So if it's negative by 35.5, then it has 360 minus 35.5 equals 324.5 degrees is the direction of that vector. Questions? That's the hardest part. Got through that. A little bit confusing. In the last class, I explained how to find it, and then I moved it and talked about from standard position like that, and I lost them. I'm glad I did it that way.
I have a question.
Made more sense. Yes.
So would it even matter if it was just maybe 5 over 7? So it's still good as the same answer, right?
Same answer. Okay. Graph the image of quadrilateral HJLK with vertices HJLK under the translation of the vector V, which has a change in x of 5 and a change in y being -5. Okay, and this is what I was talking about. So if I want to go from L to L prime, I'm just going to go in the direction of 5, 1, 2, 3, 4, 5, and down 5, 1, 2, 3, 4, 5. This would be L prime. J would be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. J prime. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. There's H prime. K is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. K prime. Check this out. These are all vectors. Right? vectors are shifting this object this way. They all have the same magnitude, right? And they all have the same direction. So we've been using vectors this whole time with our translations, correct? So I'm going to go ahead and connect them. Probably should have used a different color. Okay. So it was translated, right? Graph the image of EFG with vertices EFG under the translation of vector A and vector B. I'm going to do 2, which is the same as what we've been doing, right? Is this going to be a reflection or a rotation? It's going to be a rotation, right? Because I'm going to slide it in one direction, and then I'm going to slide it in another direction. So let's go ahead and do that. So my first vector is -4. I should say the component form of the first vector is -4, 2. So I'm going to go over 1, 2, 3, 4, and go up 2. So there's F prime. E is 1, 2, 3, 4, up 2. E prime, and G is 1, 2, 3, 4, up 2. Now I need to apply this vector, vector B. So I'm going to go over 2, up 3, over 2, up 3. There's F double prime. Over 2, up 3. There's G double prime. And E over 2, up 3. E double prime. Connect those. That's what we would call method 1. It is just a translation. So vectors, that's what I was saying, that we've been doing vectors all along. We just didn't call them vectors and didn't talk about their magnitude. And this is why. Because vectors have properties, and that's what I'm going to show you right now. So method 1 would be, I should say method 1. Method 1 would be apply vector is written like that. Apply vector A, then vector B, correct? There's a second method. No. Vector addition. So vector addition means that in component form I can add my changes in my x's, and I can add my changes in my y's. So vector A plus vector B equals, what's my change in x on my A? -4 plus 2, and 2 plus 3 would give us a new vector. We'll call it vector C, which equals
That line is for vectors.
-2, 5. And check this out. If I start here and I go back 2 and up 5, don't I end up there? Back 2, up 5. Back 2, up 5. So I could have just shifted it straight from there. It's pretty cool, huh? So those are the new vectors. Here's the original vectors. So if I add the red ones and the green ones, I get the black one. Pretty interesting, huh? And that is a transformation. It is going the same way. The resulting is a translation, but with 2 rotations. They aren't really being rotated, though. There are 2 translations for a 3rd translation. I warned you, right? Okay. I think we're done.
Next lesson.